So today we're going to be looking at how we can use process controls to manage the fluid level in a series of 3 tanks. But before we get started learning how to do that with 3 tanks, we're going to start out just deriving a simple equation for 1 tank. So if we have some sort of tank here, and in this instance we're just going to be dealing with fluids. We don't need to worry about mixing any chemicals or any substances with it. But just for the sake of being thorough, we'll consider it as if we were mixing in some chemicals or substances. So if we have this tank and it has a fluid level, and we'll call that fluid level H. And then we're going to be pumping some fluid into the tank, and that will be our flow rate in, our Q in. And then it'll also be flowing out, and that'll be our Q out. So the rate of accumulation within a tank is going to be simply Q in minus Q out. And in this case, since it's the rate of change or the rate of change in volume within the tank, we can say that the first derivative of volume with respect to time is going to be equal to Q in minus Q out. So the volume in this case is going to be the cross-sectional area of our tank times the height. So a better way to write this equation, the derivative of volume with respect to time equals Q in minus Q out, is just going to be the area. Since our cross-sectional area of the tank is constant and our height isn't, we'll say the cross-sectional area, and I'll actually call it AC just so we know what that's referring to, is going to be equal to, the cross-sectional area times the first derivative of height with respect to time. So you can see why we did that. Since volume is equal to the cross-sectional area times height, if we take the derivative of volume, we can also express that as the first derivative of height with respect to time instead of volume, and then just move the concentration or the cross-sectional area of A out. So we have our cross-sectional area times the first derivative of height with respect to time equals Q in minus Q out. And in this instance, we're going to be working with tanks that we know flow out at a certain rate, and that certain rate is going to be proportional to the square root of height. And for now, we don't know the proportion, so we're going to be calling it alpha for now. That's a terrible alpha. I'm really bad at drawing alphas. That's better. So now we can rewrite our equation. And I'll actually move the concentration of A over to the other side. Or not the concentration, the cross-sectional area. But we're going to have the derivative of height with respect to time. It's going to be equal to 1 over our cross-sectional area, and then our flow rate in, minus a proportionality constant, alpha. Oh, that was not a great alpha. Try that one more time. I'll live with that. Times the square root of our height. Now, I actually did lie a little bit earlier. We're not going to worry too much about the concentration. If we wanted to express this in terms of concentration of A of whatever substances we had, we would just have to multiply our flow rates in by the concentration of A, which we would probably denote as CA times Q in. And then same thing for the flow rate out. But since we're just going to be working with fluids and not have to worry about the substances, we'll go ahead and ignore that for now. From there, it's a really similar concept when we're applying this to 3 tanks. We just have to find the inflows and outflows to each of the tanks. And then we're going to be using a proportional control in our second tank to manage the inflow of a substance. In this case, it's just going to be a fluid, but it could be to manage the inflow of a substance, mixing a substance, something like that. So we'll talk a little bit about what a proportional control is in a minute. But for now, we're going to start off with 3 tanks. That is a really lopsided tank there. And these tanks are going to be connected at the bottom by pipes. Just pretend these lines are pipes. And then the third tank is going to flow outward into a surrounding environment. So each of these outflows, we'll label each of the outflows. We have a Q3, we have a Q2 to 3, and we have a Q1 to 2. And then we're going to be inputting into our second tank here. And each of these tanks are going to have a height as well as a starting height. So when we look at each of these Qs, each of these outflows, we're going I just undid that. We're going to have Q1, 2, we'll start with that. Well, Q1 to 2 is going, well, let me label these H2, H3. Q1 to 2 is going to be equal to, like we mentioned before, some proportionality constant, because these are outflows. So it's going to be equal to some proportionality constant. Try my hand. Wow, that was not an ideal alpha. Let me try that again. There we go. I'll live with that. We're going to have some proportionality constant multiplied by the square root of the difference in height between the tanks. So instead of just writing down our h to the 1/2, we're going to have the difference in heights between tank 1 and tank 2. Now the issue here is that if tank 2 is at a higher level, say tank 1 is down here and tank 2 is above that, we're going to have a negative term inside of these parentheses, and we can't take the square root of a negative term. However, we still want that outflow to be negative if the second tank is going to be flowing into the first tank. So the way that we can do that is, well, first off, we want to get rid of a possible negative sign within this term here, so we'll take the absolute value of that. So now we don't have a problem taking the square root of that, but in the case that we still have backflow, we want it to be negative. So to do that, we'll just use something called a sine function. All it does is take the sine of the terms inside of it, and if it's a positive term, it'll be a positive 1, and if it's a negative term, it'll be a negative 1. I believe we used this on another homework earlier in the year. So let me see if I can move these over just a little bit. And then we'll just be using that might have been a little far. That'll work. We'll just be doing the sine of the difference in heights again. Gosh, I cannot find the happy medium. There we go. So now we have the outflow from tank 1 to tank 2, and we can do the same thing for tank 2 to tank 3. So Q of 2 to 3, it's going to be the same thing. You want to take not the sing, but the sine of the difference in heights between the two tanks. I forgot a 2 up there. Between tank H2, tank 2, and tank 3, multiplied by some proportionality constant. Wow. Really not a fan of these alphas. Times the absolute value of the difference in heights again, H2 minus H3 to the 1/2. Now, the outflow for tank 3 is going to be a little bit different because we're not worried about the difference in heights between the tanks. It's just going to be dependent upon the height of the tank. So it'll be much simpler, actually. We don't need to worry about the sign because it's impossible to have a negative height of the tank. So instead, we're just going to have some sort of proportionality constant. God, these alphas. I think these alphas might be the hardest part of this course, honestly. And then we'll multiply that by our height of 3 to the 1/2. And it's important to note here that these proportionality constants might be different for each of the tanks. So we'll go ahead and denote that. This will be the proportionality between tank 1 and 2, or proportionality between tank 2 and 3, and then the proportionality of the outflow of tank 3. From here, it's fairly straightforward. We can use the same equations that we used when we were just doing one tank and find the change in volume over time for each of the 3 tanks. So let me give me a little more space here. Didn't quite mean to do that. There we go. If I can find my, there we go, the panning hand. I'm not doing this on a iPad or anything. I'm doing that on a drawing tablet, so I can't install apps natively to this. So it's kind of a goofy system here. So anyways, we have our change in volume for tank 1, and we're going to go ahead and move the cross-sectional area back to the left side of the equation for now. And you'll see why when we go to write it in Python. But each of our tanks are obviously going to still have a cross-sectional area, and the volume is still going to be the cross-sectional area multiplied by the height. So we have the difference in height over time is going to be equal to Qin minus Qout. In this case, we're not putting anything in our first tank, so we're not going to have a Qout. Instead, we're going to have 0 minus the difference between tank 1 and tank 2, which is going to be Q12. So since we don't need to write the 0 down, we're just going to have negative Q12. Can do the same thing for tank 2. The difference with this one is that we do have a Qin. We are pumping some sort of fluid into our second tank. So here we're going to have our Qin, and we'll revisit this in a second to determine how we're going to find our Qin with proportional control, minus, or actually I should say plus, we're going to be adding the inflow from tank 1 to tank 2. And then we're going to be subtracting the outflow between tank 2 and tank 3. So Q23. And then it's a very similar process for tank 3. Our Qin in this case is going to be the outflow from tank 2 to tank 3 minus the outflow of tank 3. So now let's take a look at this Qin here. So proportional control takes the difference between a desired set point of a certain tank. In this case, we're going to be using tank 3. And we're going to be using it to determine kind of how much of the fluid we're going to be putting in. So let me scroll back up here. So our Qin, and I got to get rid of my panning hand. There we go. And we have a certain point that we want our tank 3 to be at. And we'll just call it our H3 set. We might come up with a better name in the future for when we use it as a variable. But all we're going to be doing is we're going to be using something called a proportional gain and multiplying that proportional gain by the difference between our set point and our actual height. Gotta break out the panning hand again. There we go. So as you can see here, this is going to be controlling the outflow or the inflow into tank 2. Make that a little neater. So when you look at that, if we take a look at this, as we approach our set point, the difference between our set point and our actual height of the tank is going to get smaller and smaller. So the amount that we're going to be putting in is going to be getting smaller and smaller as well. So we might also write this in terms of maybe there's a constant flow that we need to have in. Maybe we want a certain amount flowing in no matter what, and then we're going to add or subtract it. Actually, that is how we're going to write it. For now, I forget the actual notation that we typically use for this, so I'm just going to write something down, and then I'll revisit it in a second. But we're going to have, we'll call it the concentration of A, even though we use that out there. And we want to add the result of multiplying our proportional control by the difference in these heights. So if for some reason the height of tank 3 were to go above our set point, this term here will become negative. So we'll actually be subtracting from our constant flow rate. And then if it's highly positive, it'll be adding more. So if we look at a graph of something like this, it'll actually end up looking kind of like this. If this is our set point, that was a really, that'll work. So it increases very sharply up into it, and this would change with a proportionality constant as well. I'll talk about that in a second. So if we have a really high proportionality constant, this term is going to have a really big impact on our flow rate. So as we get closer and closer, maybe we'll pass it. We'll way overshoot it because we have our proportionality constant set super high. So we'll overshoot it here. But then it'll start leveling out, and then it'll dip back below because, again, our proportionality constant is super high. So as the difference between the two tanks increases in the negative direction, it'll actually dip back below, and then we'll have something of not really a sine wave above and below our set point, but it'll be kind of something like that, and it'll smooth out over time. Just pretend those were straight. And then if we have our proportionality constant set really low, or not really low, but towards what we want, we'll have something more like that as it just levels out as we get to our set point. But the problem here is that we're never really going to get to our set point in that case, because as this gets smaller and smaller, it has a smaller and smaller, this right here, I forgot that you can't see what I'm pointing at. But as that term gets smaller and smaller, it's going to have a smaller and smaller effect. So we'll never quite reach our set point. We can fix this with integral control or derivative control, but we're not going to worry about that right now. So our goal is to find the proportionality constant that is going to, well, this isn't the goal of the whole task, but generally the goal is to find a proportionality constant that meets the needs that you have. So maybe you have some sort of system where you want to get to the set point as quickly as possible. So you'll set your proportionality constant really high, and you'll have it shoot straight up, and maybe you'll way overshoot it, and then it'll level out over time. And maybe you just want to get to the set point as closely as possible, and overshooting would be really bad. Maybe it'll cause some sort of spillage or something. So you will have a really small proportionality constant, or proportional control. And then you'll never quite reach there, but you'll get really close. So for now, we don't really need to worry about this extra flow rate. We're just going to say that in this case, our proportionality constant is going to be using just our proportional control, or our inflow is just going to be using our proportional control times the difference in our set point from our height. And then I'm going to go ahead and write down the values that we're going to be using to solve this. I'm just going to pull up the notes here. Give me a second. And we don't need these right now because we're going to be solving this in Python to make a graph of how these are going to behave over time given our initial conditions. But I'm just going to write them down so we can reference them easier. Okay, so we have our cross-sectional areas of the three tanks, and I'm actually going to just do this way at the bottom. Or I'll do it in that space right there. So our three tanks are going to have cross-sectional areas of, looks like 0.5 square meters. Our cross-sectional area 2 is going to be 1 square meter. And then of 3, it's going to be 2 square meters. The initial height levels are going to be the same numbers, just in meters. So we're going to have our h initial 1 is going to be 0.5. Our h initial 2 is going to be 1 meter, and then our h initial 3 is going to be 2 meters. And then our proportionality constants are going to be 0.1 for each of these tanks. And maybe in the code, we'll write it so that we can change the proportionality constant if we have a different proportionality constant between each of the tanks. But for now, we'll just leave it as 0.1, and we can change that later on. And then finally, our set point is going to be 4 meters. So now we're ready to go ahead and start programming this in Python. Again, we're just going to be simulating the dynamics of this. We're going to be basically graphing how each of these behave over time using these initial conditions, and then just letting it run from there. And one quick point of clarity, my brain was tired of writing alphas, but it looks like here we're going to just have, this is going to be our alpha. Oh, and then I also forgot to mention our proportionality constant in this case is going to be 0.1.